back on Facebook, particularly from Pat Mead and others, saying there was a problem with the audio. I checked my audio and everything looked fine on my end. All the bars were moving and I wasn't muted or anything, but some quirk of the program, it just wasn't being streamed. So restarted the program and everything looks to be fine on my end. But before I get started, if anyone is tuning in at this stage, if you just give us a thumbs up if you can hear the audio, or if there's any problems, then let me know as soon as you can, and I'll see what I can do about it. So once again, reminder, my name is Mark Costa from Organic Chemistry Explained, and I'm going to run through a few tips about resonance in organic chemistry, particularly as applied to looking at the acidity of compounds and trying to work out what is more acidic out of two particular protons within the one molecule on the basis of resonance. So if you're just joining in, we'll get started properly in a minute or two. If you tuned into the previous live and you found there was no audio, it wasn't a problem on your end, it was a problem on my end. So there was no audio being streamed for some reason from the program. So hopefully this will work fine this time. So fingers crossed, and we'll get started in a moment. Okay, so if you're coming in and you're having a look, feel free to leave a comment. Let us know how you're doing with the organic chemistry, if resonance is something that you really are looking for help with, or whether it's something that you're feeling pretty good about. And if there's any particular questions you have, then feed them into the chat. This is still a very new thing for me, and I have had some technical problems with the chat as well. So, but if I do see any unanswered questions after the live stream, I'll go back onto Facebook and YouTube and everywhere else this is streaming and try to answer your questions in some way there. Okay, so let's just go over to the topic. So resonance and acidity. There's a few things that I want you to think about when thinking of resonance. So the first thing is that you can display resonance. You can look at resonance by drawing curved arrows to show how one resonance form is related to another. So my first tip with resonance is to use curved arrows. Okay, and an example of this would be if we have a carbocation like this and a double bond, we could draw the other resonance form, which is this, but it really helps if you draw the curved arrows to show how one relates to the other. So we're going to move a pair of electrons from this pi bond to make a new pi bond and to make the positive charge hop over to the other end of the chain. And curved arrows are where we show the movement of electrons. Resonance, we show the relationship between two, I'll use a different color for this. We show the relationship between two structural formulae. We show that they're resonance contributors to an overall structure by using this double-headed arrow, resonance arrow. Okay, so my second tip is that we need to have an uninterrupted pi system for resonance to occur. So we need uninterrupted p orbitals, really, is the important thing. And so we get out of that a pi system. And we would call that a delocalized pi system, or delocalized charge if there's a charge involved. Okay, and why is this? Well, we need to be able to have all these overlapping one after another to be able to get this delocalization, or this conjugation or resonance. There's a few related terms here. So if we have carbon atoms, or atoms of any type, where we have adjacent p orbitals like this, then we are going to be able to draw resonance structures between those. If we have, for example, a pi bond and then an adjacent negative charge, that would be this, and so we can draw resonance forms where what we're really trying to show with the resonance structures is that the two electrons of the negative charge could be sort of shown like that, and the pi bond could be between those other two atoms there like that. Now that's the orbital look of this, which is sort of not really great to be mixing in with resonance. Resonance is a different concept. Resonance is more about just drawing our normal bond line structures and saying that if we have a situation like this with a negative charge, then we have a sp2 hybridized atom here, sp2 hybridized there, sp2 hybridized there, and we can have a pi system between all of them because there's p orbitals. And so we can get our resonance form like that. Whereas if we have a different situation, so for example, if we have a double bond and then we have a negative charge here, there's a problem because this carbon in between has hydrogens attached to it to make it have its octet, and so that is sp3 hybridized, and that interrupts the conjugation and it interrupts the ability to draw other resonance forms. So there's no resonance forms available for this one that delocalize that negative charge. So it's not possible. The final tip that I would say for resonance is around stability. Oops. So stability. In terms of stability, more is better. Okay, so the more resonance forms you can draw, the more stable the molecule is. And particularly if there's negative or positive charges involved, because the ability to draw resonance forms where that charge moves to a different atom shows that that charge is smeared out or spread out over multiple atoms. And nature abhors having a charge on a small space. So if we can spread it out, that's energetically favorable. The other thing is that more stable resonance structures are more important. So if we draw two different resonance forms and one by itself is much more stable than the other, then we know that the more stable form will be the more important one and that will contribute more to the overall structure of that particular species. So let's go through a few examples to show how this works in terms of acidity of compounds. What is a more acidic compound than another, or what is a more acidic proton within the one molecule? So here we've got an alkene, and I'll draw in blue. Removal of this proton here will give us a anion with a lone pair of electrons and a negative charge there, and then our double bond is out here. And so we've drawn in the one hydrogen in red that we could take off, but let's draw in the two that are attached there, neither of which were removed to make this anion. So that means there's an sp2 hybridized, sp3 hybridized atom in between the negative charge and the double bond, and so resonance is not possible in this case. And so therefore, there's nothing to help stabilize that negative charge in terms of conjugation or delocalization. If we compare that to the red case, we've got this position would have the negative charge. Let me just redraw that. And it's right next to the pi system of that alkene. And so in terms of resonance, we can draw curved arrows that show how we can get to a different resonance contributor. So here's our double-headed arrow for resonance. Here's our structure. We've moved from this carbon to make a double bond there like that, and then up here to put the negative charge on that carbon there. So we've spread out the negative charge over two different carbon atoms, so this is more stable. And so therefore, this is the more acidic proton. Okay, so why is it more acidic? When we remove that proton, we get a more stable anion because there's two resonance contributors. And therefore, the equilibrium between the protonated and deprotonated side will shift a little bit further toward the deprotonated side in the presence of a suitable base. And so that stabilization of the conjugate base, this anion, helps to make the conjugate acid, this one here, that proton more acidic. Okay, so let's look at the next example. The blue proton here is attached to this nitrogen. So we've got a nitrogen with a methyl group. If we remove that proton, we'll end up with a negative charge and a lone pair of electrons on that nitrogen. We go up to a benzene ring like this. And then nitrogen is unchanged here. And so in this case, we've also got an sp2, keep on getting that one wrong. We've also got an sp3 hybridized carbon in between the lone pair of electrons on this nitrogen and the pi system of the benzene ring. And so that interrupts and stops the ability for this to be stabilized through resonance. There's no resonance possible there either. Okay, let's compare that to the red proton. If we pull that proton off, we're going to get a nitrogen with, we're getting a nitrogen with a lone pair of electrons and a negative charge. I've drawn this slightly different there. Let me just redraw this. Negative charge methyl group up there. We go down to a benzene ring like this, and then this bit is all unchanged, so we'll just draw it out. And that negatively charged nitrogen is right next to the pi system of the benzene ring. So we can draw resonance contributors where we push electrons like that onto the ring. So if we drew out that resonance contributor, we'd end up with the negative charge would be here. So I'll just draw it like that. And then we would have a double bond to this nitrogen, bond up to that methyl group there. And then this bit down here is not important. And then, that's a double-headed arrow. Okay, but we can also draw other resonance contributors to this structure. So we can push this pair of electrons out onto this position here as well. And so that will give us another one we can draw, which is like this. Lone pair of electrons and negative charge on that carbon atom. We would have double bond there, double bond there, double bond nitrogen there, and so on. So there's our double-headed arrow. And then finally, there's a third one we can draw where we push that pair of electrons here and then there. And what we're going to get out of that is the negative charge is now going to be on this, sorry, not that one. It's going to be on this carbon atom here. Double bond, not there. Double bond is going to be there and there. Double bond to nitrogen. Then we're going to have this going down there like that. And so we've spread out our negative charge over 3 different positions around this benzene ring. And so all 3 of those resonance contributors are helping to stabilize this anion, spreading out that negative charge. And so this is highly resonance stabilized. Okay, if we go back to our terminology around acids and bases, it's a resonance stabilized anion, and this particular anion we would call the conjugate base. So it's the conjugate base formed when we remove this red hydrogen here, and by stabilizing that conjugate base we make the acid it's derived from more acidic. So this is the more acidic proton in this case. Okay, let's go to the next example here. So if we pull off this proton here, we're going to get a molecule. Let's, where should we do it? We'll just do it down here maybe. We'll get a negative charge there, double bonds. And can we draw resonance contributors? Yes, we can. In this case, we're going to move them here like this and onto that position. And we will get the negative charges on this third carbon on the ring. Double bond there, double bond there. Now, I'm going to leave it for you as a bit of homework, a bit of practice. Can you draw all the other resonance contributors for this? What you're going to do is you're going to keep on moving that lone pair of electrons like this, and then on to the next position, and so on. And what you'll find is you can draw 5 resonance contributors for this particular species, this cyclopentadienyl anion. And so that makes this anion, even though the negative charge is on carbon atoms, it actually makes it very stable. There's another factor called aromaticity. You may or may not have come across it in your course. It's not really something we want to cover in this particular live session, but it also is adding to the stability of this anion. But overall, it's very highly resonance stabilized. Now, if I compare that to take off the red proton, what I'm going to get is a species with the negative charge here and the double bonds here like this. So the negative charge is actually on a carbon that was already sp2 hybridized. And when that carbon is sp2 hybridized, it means that it's using its sp2 orbitals, its sp2 hybridized orbitals, to make a bond to that hydrogen, a bond to this carbon, and a bond to that carbon there. And so when the negative charge is formed, that lone pair of electrons is in an sp2 hybridized orbital. So what does that look like? If I draw out this in a perspective sort of manner, I'm going to have that sp2 orbital is going to be like this. It's in the plane of the ring. Okay, so I've got my pair of electrons like that. And then that's quite different to the pi bonds that make up the double bonds within this ring. So each one of these atoms has a p orbital that is overlapping with the carbon next door to make what look like two double bonds, although it's actually a delocalized diene. And those p orbitals are orthogonal to the sp2 hybridized orbital that has the lone pair of electrons from this anion in it. And so we don't get conjugation between them because they're at right angles to each other. And so this anion can't benefit from delocalization, and we can't use resonance to show how we could stabilize it. So we say no resonance, stabilization, just shorthand that, of the anion. Okay, and therefore there's no delocalization of the charge. Whoops, delocalization. Okay, so that means that overall this blue proton is going to be the more acidic because we've got the more stable resonance stabilized, delocalized anion is formed when we pull that proton off. Okay, let's look at a few more examples and then we'll call it a day for this live session. So now we've got some structures with oxygen in them. The first one here, when we take off the blue proton, we're going to get a structure with carbonyl group there, lone pair of electrons, negative charge, and it looks like this. And when we draw our resonance contributor, we're going to push electrons like that, push them out onto the oxygen, and what we're going to get out of that is a molecule with the oxygen having 3 lone pairs. It had 2 to start with that weren't drawn in, and a negative charge, and we're going to have a double bond to this carbon atom here, like that. And so overall, this is resonance stabilized. There's stabilization of a negative charge, that's good. And then let's look at the other possibility. So in red, we've got the possibility of having carbonyl group there, and the lone pair of electrons, negative charge would be on that carbon atom. And what we've got is, once again, interruption by an sp3 hybridized atom. So that sp3 hybridized carbon atom is stopping us from drawing valid resonance structures, or if we look at the orbital point of view, it's stopping the direct overlap of p orbitals between the negative charge on carbon and the pi system of that carbon-oxygen double bond. And so that's not resonance stabilized. Okay, so now there's one other thing I wanted to point out about this first case in blue, and that is that in this case we've got the negative charge is on oxygen, whereas in the first resonance contributor the negative charge is on carbon. Now, what do we know about oxygen and carbon? We know that oxygen is more electronegative than carbon. So oxygen is actually quite happy to have that extra electron density. And so the more important resonance contributor in this case is the one that has the negative charge on the oxygen atom. So we would call this the major resonance contributor. Or you might call it the more important one. And it tells you something about the structure. It tells you that if you looked at where the charge is, it would be partly on the carbon, partly on oxygen, but actually it would be unbalanced. There'd be a lot more of the negative charge on the oxygen than the carbon because oxygen is electronegative. And so overall the structure would look more like the one on the right than the one on the left, even though it's going to be a hybrid of those two. Okay, let's look at the next example here. We've got a carbonyl group. We pull off the blue proton, we'll get a lone pair of electrons and a negative charge there, and we're going to have our carboxylic acid at the end of the chain like this, and then we can draw a resonance form where we have that carbonyl group. Oxygen has 3 lone pairs and a negative charge, and it's just like the previous example. So I'll go through this very quickly like that. Okay, we can draw our curved arrows if we wanted to show how we get from one resonance form to the other. Now the red one, what does it look like? It's going to have the carbonyl group is going to be unchanged, so let's just draw that in. And then the carboxylic acid is going to be like this, and we're going to pull off that red proton, so we're going to have oxygen with its 3 lone pairs of electrons and a negative charge. So it's going to have that structure there. And then when we want to draw the other resonance contributor, we're going to draw curved arrows to get a pair of electrons, move it like that, move it on to the oxygen atom. Okay, the carbonyl group there is unchanged, but we'll have a oxygen here with 3 lone pairs and a negative charge, and then a double bond to that oxygen like that. Okay, so they're the 2 resonance contributors. Now once again, we've got, in this case, we've got 2 oxygens with the negative charge. In this case, we've got 1 carbon and 1 oxygen with the negative charge. So which one do you think will win? The one that's going to win is where we have the negative charges shared in both resonance forms on the electron withdrawing oxygen atom, because oxygen is so much more capable of bearing a negative charge. And so this is the more stable species because both resonance contributors have the negative charge on an electron withdrawing oxygen atom. And so because that's more stable, that means that this proton is more acidic. Okay, and I forgot to point out before that we said that this one here would be the more acidic in the case of a ketone. Acidic, the one that's, we call that the alpha position, because we start counting using Greek letters as we move away from the carbonyl group, and so the other position with the red hydrogen would be called the beta position, or beta. Okay, down to our last example, we've got a benzene ring with a blue proton attached to an oxygen versus a red proton attached to a carbon atom. So let's look at the blue first. In the case of the blue proton, we would be getting a structure that would have an oxygen atom with 3 lone pairs and a negative charge like that. And that would be unchanged. And then we could start drawing our resonance contributors by moving the electrons around the ring like this. And we would get to our first possibility would be where that lone pair of electrons and negative charges on the ring carbon like that. And we would now have a double bond to oxygen. It would be back to only 2 lone pairs. And then our alkyl group would be there like that. Okay, so we can, like before, when we have benzene rings, we often have the ability to really delocalize that charge over many positions. So we could draw other resonance contributors where it goes around to this carbon here. And then from there, we could use another one. I won't draw it in, but we could draw another one that puts the negative charge on that one there. Okay, so I won't draw these in, but we'll have 3 resonance contributors. Well, 3 resonance contributors, or 3 resonance structures where that negative charge has been placed onto a ring atom, which is a carbon atom. And then we've got 1 over here, which has the negative charge on an oxygen atom. Okay, now if we compare that to the red case, in the red case we're going to get, this will be unchanged, but we'll have the negative charge here like this, and then when we draw our resonance contributors, we're going to push this onto the ring like that, and we're going to get something that looks like, we're going to have a double bond there, and we're going to have our lone pair of electrons and negative charge there, and then that like that. Okay, we can do the same thing. We can start pushing that further around the ring onto this position, and so on. Okay, so in that case, if we do that, I won't go through it all in this live session, but there will be 3 resonance contributors with the negative charge on carbon. And that's just like before. Oops, we've skipped ahead a page there. Sorry about that. So it's going to be on carbon. And then we've got 1 over here where the negative charge is also on carbon. Okay, so that's the external carbon atom that we first started with when we pulled off that proton. And so overall, the more stable structure is going to be the one that on the left here in blue, where one of the contributors has the negative charge on an oxygen atom, which is electron withdrawing and therefore able to stabilize that negative charge better. And so this will be the more acidic proton in this case. Okay, so that's all the examples I wanted to show you. Just to recap, resonance really important in terms of not only stability of compounds like this, but a lot of other things we talk about in organic chemistry rely on this idea of molecules not being best represented by just one structure, but by multiple structures. In terms of resonance, you really want to be using curved arrows to show how you can go from one to another. You want to look for uninterrupted p orbitals, so carbon or other atoms with p orbitals that are next to each other, one after another, contiguous, with no interruption by sp3 hybridized atoms. In terms of stability, the more resonance contributors you can draw, the better. And the resonance contributors that you draw that are more stable are more important and tell you more about the overall structure than the others. And so, for example, if you can put a negative charge on an electronegative element like oxygen, that's a more important contributor and more stabilizing than contributors where that negative charge is on a less electronegative atom, like, for example, a carbon atom. Okay, so leave a comment below the video if you have any other questions. If you're interested in other videos like this and you're not already part of the Organic Chemistry Help Facebook group, then please join. Please subscribe to my YouTube channel, Organic Chemistry Explained. Come visit my website, organicchemexplained.com, interactive tutorials and other bits and pieces for you there. And you can get onto my newsletter and I'll send you out useful information for your organic chemistry studies. And keep an eye out for more of these live sessions. And please let me know if you've got particular things you'd like me to talk about again in the future. Okay, have a good day and good luck with your studies. See ya.